Hello, my name is Ji Ye. I'm a first-year PhD student majoring in computer science at Illinois Tech under Dr. Xianhe Sun and Dr. Kukas Anthony. My research interests are including L integration of HPC and the big data storage system and L optimization. Today, my presentation topic is HDF5 wall connector to Apache Arrow. This project is supervised by Dr. Banasrin and Quincy Cozio. I'm very glad that I can have this opportunity to present this work. This slide gives the outline of today's topic. First, I will introduce the problem statement. As we all know, scientific data is often organized as the structure of arrays or array of structures. Structure of arrays is a layout separating elements of a record into one parallel array per field. The left feature shows the layout of the SOA. In SOA, each member of all instances next to each other. This structure is good for vectorization, but less good for data locality. When only a subset of members is needed, this structure is very good. However, array of structures is the opposite layout in which data for different fields is interleaved. The right finger shows the layout of the LIs. For this structure, all members of each instance next to each other. It's good for data locality, but less good for vectorization. This structure is good when only a subset of members. This structure is not good when only a subset of the members is needed. HDF5 works well with the structure of SOA. However, it performs suboptimal when dealing with array of structures and table-like data structures. Data access are always column-oriented. In these structures, data access are always column-oriented. This would cause transformation when column data is required. Recently, Apache Foundation released an in-memory column store called Apache Arrow, which is considered as an efficient in-memory column store data management in cloud environment. Apache Arrow is an open source column in-memory representation that enables analytical systems and data structure to exchange and process data in real time. It specifies a standard columnar file format for representing structured table-like data set. It also creates a memory column store that can be used to manage streamed data. Now it has been widely adopted in cloud computing and big data analysis community due to its high performance. In addition, Apache Arrow libraries are available for many languages like C, C++, Go, Java, Python, and so on. This is the official website of Apache Arrow. You can find a lot of information and use cases in its website. Here are some advantages of Apache Arrow. First, first column is fast. With a column format, it allows computational and execution engines to maximize the efficiency when scanning large chunks of data. It also enables vectorization using the SIMD operations. Second, with the Apache Arrow, it could reduce the overhead of copy and convert when moving data from one system to another. Like these two figures show, without Apache Arrow, when different applications want to exchange data, they need to copy and convert the data into its own structure and then perform computing analysis, because each application may have their own data representation structure. This process will add a lot of overheads. However, with Apache Arrow, we when different. However, with Apache Arrow, they don't need to copy and convert when moving data from one system to another. In turn, this will reduce the overhead. That's why more and more applications in cloud computing and big data analysis community plan to integrate Apache Arrow. Um, as we said before, Apache Arrow is an efficient in-memory data management column store. Therefore, to evaluate how big data technologies that offer new capabilities work in HPC systems, and to use Apache Arrow directly from HDF5, we developed an HDF5 work connector to Apache Arrow. Uh, the red finger shows the location of Apache Arrow within Vol connector. We can see it's a terminal Vol connector, which is the last layer in the connector stack. Through this Apache Vol connector, it can also bridge the gap between sense applications and analytic tools that use HDF5 and and the Apache Arrow data. Next, I will introduce the design of the Arrow Vol connector. Uh, this slide shows the internal workflow in Arrow connector. In our design, each MPI rank will write its specified subset region as an Arrow table to the backend storage or Arrow flight server. Here, the backend storage includes local file system and Plasma store. Plasma store is an in-memory object store provided by Apache Arrow official website. Arrow Flight is an RPC framework provided by Apache Arrow for high-performance data services based on Arrow data. It is built on top of the gRPC and the IPC format. With the Arrow Flight server, it enables two different applications to communicate in near real time. As this figure shows, when Arrow receives um, a write request from a H5 write application, it will create an internal column major buffer in memory, then convert the row major into data into column major and save it in the internal buffer. Here we need to convert the data from row major into column major because HDF5 store data in row majored, but Apache Arrow store data in column majored. When receiving the close request, Arrow will flash the metadata and the data into the backend storage. In the right side, when receiving the read operation, Arrow will first read data from the internal buffer will first read the data from the internal buffer and convert the column major into row major to the output buffer. If the data is not exist in the internal buffer, it will need to load data from the backend storage to the internal buffer and then convert the data from the column major to row major and fill the output buffer. Next, I will show some initial write and read performance results when writing and reading data with Arrow and without Arrow. The experiment is performed on Cori Supercomputer. During this experiment, I used 8 nodes and 128 processes. This test stores a native HDF5 file and Arrow file in raster file system. The strap size is 16 megabytes. For Arrow, the strap count is 1. Because each MPI rank will write a file. For native HDF5, the strap count is 8, since all processes will write a single HDF5 file. I tested the 3 different 2D array compound type physical particles data sets. The size of particles are 4 megabytes, 8 megabytes, and 60 megabytes. These are the data spaces of each data set. The benchmark I used in this experiment is H5 bench write and H5 bench read. H5 bench has a lot of different L patterns. During this experiment, I tested 2 different L patterns for H5 bench write and H5 bench read, respectively, which are CI and IIL patterns. As the table shown, CIL patterns means that contiguous in memory and compound in file. While IL patterns means that compound in memory and compound in file. These 2 columns shows the memory representation and file representation for different patterns. For contiguous data, different data are organized contiguously in different arrays. For compound data, different data are organized in one data set. The data are interleaved each other. For H5 bench read test, I performed 2 different tests. One is reading the entire data set, and the other one is reading a subset of the data set. This slide shows the write performance result. The left finger shows the row write rate, while the right one presents the observed write rate. Here, the row rates are calculated as a ratio of size of data and the row times, while the observed rates is calculated as a ratio of the size of data and the observed times. The row times are the wall clock times for performing a read or write operation, while the observed times are the time that overall benchmark observes. From the left one, we can see only Arrow performs better than native HDF5 in all data sets when the accessing pattern is CI. For native HDF5, some data may haven't flashed to the disk, but for Arrow, the data has been flashed to the disk in this stage because Arrow flashed the data when receiving the H5 declose request. Well, according to the observed write rate result, Arrow always performs better than native HDF5 in all data sets for both CI and I patterns. So for the write performance, Arrow is a little better than the native HDF5. This slide shows the read performance result when accessing pattern is II, which means the compound in memory and compound in file. For read, I tested 3 different use cases. The first one is reading the entire data set, and the second one is reading a medium size columns. The last one is reading a small size columns. In the read operation, Arrow needs to read data from disk. From these 2 figures, we can see that the performance of Arrow is almost the same for each data set. The read performance of native HDF5 is higher than Arrow. The performance of Arrow better than native HDF5 is only in the situation when reading small size columns. When reading the first possible reason is that Arrow needs to convert the column-wise data into row-wise when reading the data. This will add a lot of overhead. The second possible reason is that native HDF5 may have some optimization when reading the data. Similarly, this slide shows the read performance result when the access pattern is CI, which means contiguous in memory and compound in file. For this pattern, I also tested 3 different use cases, and Arrow needs to read data set from disk. Similarly, from these 2 figures, we can see that the performance of Arrow is almost the same for each data set. Only reading small size columns perform better than native HDF5. It has the same conclusion as the IL pattern. To summarize, in this work, we designed and implemented an HDF5 wall connector to Apache Arrow that enables sense applications to access Apache Arrow data through native HDF5 cores without changing the original code. It verified how big data technologies that offer new capabilities work in HPC systems. We have shown some initial performance results when using Arrow wall connector. Although the performance is not very good, but there is still a lot of room for optimization. More importantly, this work laid the foundation for our future work. So questions?
Thank you. We're running a little bit low. Just time for one question.
Hi, I have one. With how many fields did you test?
How many what?
Fields or columns in case of Apache Arrow. One structure, how many columns?
I use 8 nodes and 128 processes to test the data set.
The structure.
The number of data sets is 8. Or fields is 8.
8 fields.
Yeah.
8 fields, so 8 columns.
Yeah, 8 fields.
Yeah.
Each particle has 8 fields.
Okay.
And just one comment, if you are going to make this wall connector public, which I would encourage you to do, please register with the HDF group so we can assign you a number and people will be able to use it using, identification number, like with filters, when you are ready.
Yeah. Now the code haven't fully completed. When it is fully completed, we will maybe public them.
It's okay. When it's ready, I think many people will be excited to use it.
Yeah.
Thank you.
Yeah, I had a question. So what happens when the amount of data exceeds the amount of memory? Is this just not supported, or how's it handled?
Maybe I can briefly answer that. We are planning to dump the data to the Parquet file or Plasma store. Use that as a memory mapped file so that it is still connected.
Right, but you need let's see, like when opening, do you need to move the entire contents to memory?
Let's leave it for discussion. We have presentation ready. Thank you.